So today we're going to be going over project 2 with the flat plate and analyzing the boundary layer. So right now we're at the point where we just exported everything from Fluent and into a Excel sheet, and we get the position. So here we've translated to simpler coordinates up to 1 meter, and then here we have the wall shear stress and the skin friction coefficient. These two are from straight from Fluent. What we're going to do, we're going to calculate it theoretically using the Blasius equations, and we're going to see the differences. So to start off with the wall shear stress, I've already written down the equations to make it quicker, so I'm not writing it down on the spot. But here we have the wall shear stress, and so yeah, it's 0.332 times the viscosity, well, the square root of the viscosity times the square root of the air density times the free stream velocity to the 3/2 power over the square root of the position that we're at on the flat plate. So when we get that, this number right here, and what I'm going to do, I'm just going to drag all of this down to calculate what we have. And yeah, as we see, the wall shear stress is decreasing, and in the Fluent, the wall shear stress is also decreasing, and the final numbers are very well, pretty similar to each other, 0.00469 and 0.00434. So there's a slight discrepancy, but as expected from simulations versus calculations. All right, so moving on to the skin friction coefficient. This equation consists of 0.664 over the Reynolds number in the x direction. So yeah, right here we have all the components of that. And the Reynolds number, I'm just using rho v x over mu. So here it is. And we get this number right here. I'm gonna drag it down to expand that and paste it onto all the cells. And this is the other skin friction. We could see, for example, at the beginning, it starts at 0.08. This one starts at 0.01. So there's like more of a difference, but that's what we could expect. Also, just heads up for reference, the beginning ones I've already put for these, and I've matched them to the skin friction and the wall shear stress for the Fluent measurements, because when calculating using the Blasius equations, you're dividing by the Reynolds number, and when you try to get the Reynolds number at 0, you get well, you're going to infinity, so it's not fun. And I was gonna put it at 0, but I just felt like it would be better to start both of them at the same place for the graphs. So that's the explanation for that. All right, so moving on, we're gonna look at the theoretical boundary layer. So for the boundary layer, we use, again, the equations, and it is 5 times the x distance on the flat plate divided by the the square root of the Reynolds number, and on the x direction. And here we go. This is the equation. I'm gonna drag it down again. And moving on to the drag coefficient, we have pretty similar 1.328 over the square root of the Reynolds number. And here we have it. We're going to drag that down. And the drag coefficient is also going to vary throughout the distance of the flat plate. So, all right. So what we first want to find out, we have the x positions that we want to find. So at 0.25 meters, which is 25 centimeters, and then 50 centimeters and 75 centimeters along the flat plate. And we want to compare the Fluent boundary layer thickness versus a theoretical boundary layer thickness. So here for the boundary layer thickness, we're going to look right here in this column. So we're going to go over to yeah, and as you can see, R is increments in terms of like 0.02. So we're going to look at these two, and we're going to interpolate between these two values for 0.25. And what I got after that was 0.006565 meters. And the 0.5 to find is much easier. It's this one. Okay, so it would be right here. So we get 0.9682. Okay, so here we're gonna go to 0.009682. And for the last value of 0.75, we're also going to interpolate. Oops. We're going to interpolate right here again between these two values for the boundary layer thickness, and we get 0.011858. Sorry. All right. So right here we have these three values, and to see the relationship between them, we could, it's right here. Obviously in the submission, I've changed the title of the graph since it looks kind of funky, but here it is, the relationship between the boundary layers for Fluent and for the theoretical one. Oh. Okay, so moving on, we're going to want to see the relationship here. I have it, I'll graph it or plot it again, but the simulated versus the theoretical wall shear stress along the flat plate. So we want the shear stress. So what we're going to do right here, we're going to highlight all of these, and we're going to get rid of this column, and we're going to insert a graph. I'm going to do one of these. Okay, so here we have it. Here the x coordinates are the position along the flat plate up until 1 meter. We could see that both of them have the same kind of trend, but they have different slopes at the beginning. So there's a slight difference between both of the values. All right, I'm going to delete this. Next up, what we wanted to look at, the relationship was the theoretical versus simulated skin friction coefficient along the flat plate. So once again, we're gonna see the skin friction right here. Drag it all the way down. And since we want the skin friction, we're gonna get rid of this wall shear stress and the wall shear stress. And same as last time, we're going to do this. So as we can see from the graph, of course, the x coordinate is the position along the flat plate, y coordinate, skin friction coefficient, and here's the relationship. The theoretical one drops off way quicker, and it kind of stabilizes way quicker and way lower, like closer to zero than the Fluent does. So there we have that. And the other thing we wanted to look at was the drag coefficient. I have it graphed here, but I'll just do it again. So I'm gonna go here, and then I'm going to get rid of these, insert, do one of these. And here we have it. Yeah, so for this one, I didn't change it from I just left it at 0, but we can kind of get rid of that, and we see that the drag coefficient starts and then it starts decreasing and then levels out at the end. So it's kind of similar to all the other graphs, but that's to be expected. The boundary layer isn't really going to exponentially increase. Like it's going to stabilize somewhere, and then all the values are going to also stabilize, and then the the length just ends. Oh, this was for this, so um, give me a second. Oh, okay. Well, kind of messed up there, but we still have the relationship here until 1. So what I was saying, it just stabilizes. The boundary layer is gonna be developed near the end, and then the plate just cuts off there. So that's where we stop our measurements, and that's where it stabilizes. So there we have that, and that will be the calculation tutorial for project 2.